Hi there, this is the answer key for the dynamics hand-in for Physics 30S. So question number 1 says, whiplash sometimes results from an automobile accident when the victim's car is struck violently from the rear. Suppose a car is struck at rest from behind. Explain why the head of the victim seems to be thrown backward in the situation, and is it really? And the answer is, the head is not thrown backward. The car's seat pushes the body of the person forward, but the head has nothing to push it with. So it stays in place according to Newton's first law. Eventually the neck pulls the head forward. Since the seatbelt holds the body in place, not the head rushes forward, resulting in whiplash. And the headrest should be directly behind your head to prevent this from happening. I mean, there's a video here that you can click on as well to see that. Basically, it looks like this, right? Here's the seat, and here's the person's head, and their body sitting in the car, right? And as the car is pushed forward, what happens is the seat moves forward, the head stays at rest, like so. Painful. And then, of course, eventually the neck, your muscles in your neck will stretch, and then eventually they reach the end of what they can stretch, and then the head is whipped forward like this. The seatbelt holds the person in place, nothing to hold the person's head in place, and so their head goes forward after that, causing that whiplash. And so what needs to happen is you need to have your headrest of your seat needs to be there so that your head cannot go back, and that will keep your head safer in a car crash. So you should adjust your headrest as well when you get in a car. All right, question number 2. If the acceleration of a body is 0, are there any forces acting on it? Explain. Well, there could be 0 forces on it, but since most of the universe is affected by gravity in some way, it's likely that there are multiple forces. These forces, however, are balanced, so the net force is equal to 0. So even if it's not on, it is on a surface, then we quite likely have a weight force and a normal force, and they're balanced. Even if it's in free fall of some type and there's a weight force, quite likely there's some sort of air resistance, and those forces again would be balanced. So yeah, there's probably forces on it. They're just balanced. Why do you push harder on the pedals of a bicycle when first starting out than when you're moving at a constant speed? And this one students always have some trouble with, so I'm going to try to explain at the start. At the start, there's going to be some friction. There's going to be friction when you're already moving as well. Okay? The difference is here that you are accelerating. Right? And so your net force has to be what I'm going to call the applied force, which is going to accelerate you, plus you have to provide enough force to overcome friction. Down here, when the bicycle is already moving, the net force, you no longer need to apply the force to accelerate. You're already moving at a speed. Your speed is constant. You only need to provide as much force as friction is needed. Now, it is true that static friction is greater than kinetic friction, so this actually friction force right here would actually be bigger than this one. But the main reason is because at the start you are accelerating, and force is required for an acceleration. In the lower situation here, the man is already traveling at a constant speed. No need to accelerate. Only friction force is needed to overcome. Okay, a 5 kilogram object is accelerated at 2 meters per second until it attains a speed of 10 meters per second. So here it's going 0, here it's going 10 meters per second. And the acceleration is 2 meters per second squared. At that time, it continues to move at 10 meters per second. So it's going to continue moving. Didn't mean to do that. It's going to continue moving at 10 meters per second. And at this point right here, my friction force is 8 newtons. What force is required for the object to continue moving at 10 meters per second? Don't get fooled. This is a velocity. It is not an acceleration. And so what force do I need? Well, I need a net force of 0. 5 kilogram object, it is not accelerating anymore. My net force is 0. So now when I go F net is equal to Fa plus Ff, just like in the bicycle question before, what is my net force? My applied force, the F net here is the 0, right? What is the applied force? Well, it's equal to the friction, just in the opposite direction, right? This 8 goes to the other side. 8 newtons is equal to my applied force. That's how much I have to apply because my net force is equal to 0. A .145 kilogram baseball traveling at 40 meters per second, so the baseball's coming into the baseball glove like this, strikes the catcher's mitt, which in bringing the ball to rest recoils backward about 12 centimeters. So the mitt goes backwards about 12 centimeters, or 0.12 meters. What was the average force applied by the ball in the glove? Show your work in an organized fashion. All right, so there's 3 steps here. The first step is to calculate the acceleration, which is delta v over delta t. The change in velocity is going from 40 to 0, minus 40. That's probably worth 1 mark. I probably should have shown that. Delta v is vf minus vi. 0 minus 40 is my change in velocity. So I've got minus 40. My time is, I don't know my time. Why do I not know my time? I need to do this. I need a first step before that, don't I? You should have to use an eraser. I'm lucky I don't. I'm going to have to do this. V bar is equal to d over t. What's the average velocity? Oh, I got to calculate that. Good thing I left space up here. 40 plus 0 over 2. The average velocity is 20 meters per second. So 20 meters per second is equal to my displacement, 0.12 over my time. I get a time of 0.006 seconds, which seems pretty reasonable. Gloves catch baseballs in a very short period of time. Remember here, my delta v is 40. It's not the 20. So now use this time right here, 0.006. And that gives me an acceleration of 6,666.7 meters per second squared. And yes, that's a really big number, but it's a really big acceleration. Now I use my F equals ma. The mass of the baseball is 0.145, because it must be in kilograms, multiplied by that 6,000 number, and I get minus. Now why is it minus? This should actually be a negative here. This should be a negative here. It's minus 966.7 newtons. I think that's a little unreasonable. I've got my numbers mixed up there, but that is indeed the correct answer. 966 newtons is quite a bit, of course. Okay, number 6, according to a simplified model of the heart of a mammal, at each pulse, approximately 20 kilograms of blood is accelerated from 0.25 to 0.35 during a period of 0.1 seconds. What is the force exerted by the heart? Show your work in an organized fashion. First step, calculate the acceleration. And I'm going to do my delta v in one step right here. I'm going to go 0.35 minus 0.25 all over 0.1, which is 0.1 over 0.1, which is an acceleration of 1. And that makes things very convenient, because now I can go F equals ma. 0.02, you got to convert that to kilograms, times 1, 0.02 newtons, which is quite a small number, 0.02 newtons. All right, number 7, you're testing the braking of a new design of a vehicle. The car has a mass of 1,500 kilograms, and the brakes at their maximum exert 7,500 newtons of braking force. Calculate the table, complete the table below, and construct a graph of braking distance meters versus speeds on graph paper. So the first step is to convert all of these kilometers per hour to meters per second. I'm just going to write these numbers in. Remember, you would divide by 3.6. So I've got 13.8, 22.2, 27.8, 30.6, 33.3. The force stays the same. The acceleration, because F equals ma, is 7,500. The mass of the vehicle remains the same. My acceleration is going to be a constant minus 5, or 5, I guess, depending on whether you're braking or accelerating. So I'm going to put 5 all the way down there. How do I calculate the time? Now I go A equals delta V over delta T. 5 is equal to my change in velocity. If I'm going from 13.8 to 0, that's minus 13.8 over my time. Here's where the acceleration has to be negative so that your time is a positive value. 2.76. You would do the same thing for all of these. 4.44, 5.56, 6.12, and 6.66. How do we calculate the braking distance? V bar equals D over T, but I need my V bar. So it's going to be in the first case, 13.8 plus 0 divided by 2. That's going to be 6.9. And now I'm going to go V bar is equal to D over T. So 6.9 is equal to D over my time, 2.76. And I get a displacement of about 19 meters. I think there's some rounding going on there. So you get 19 meters, 49.3 meters, 77.3 meters, 93.6, and 110.9. And when you graph it, you should get a graph that looks like this. One or two people may have had their X and Y backwards. You should have braking distance here, and you should have speed down here on the X. All right, number 8. Suppose Mr. Bennett is on a bike with his dog Buster. Buster is chasing a squirrel like he always used to, and accelerates Mr. Bennett by pulling on his leash. Hopefully I'm wearing my helmet, because I do not want another concussion. Draw a free body diagram for Mr. Bennett on his bike. Include all forces on him. Assume that he and the bike are one object only. So I am represented by me and my bike by this box. There is a regrettably substantial weight force on me. There is a normal force, which keeps me from falling into the ground. There is a small amount of friction, and then there is a gigantic applied force as Buster chases the squirrel. And the red one here, the applied force, is much greater, causing me to accelerate, much greater than the friction force. And the last question, what is the acceleration of a model airplane moving horizontally on a table if the engines produce 150 newtons of force and there's 25 newtons of air resistance? Include a free body diagram to ensure your work in an organized fashion. All right, so I've got my model airplane. It's on the ground. Got a weight force, got a normal force, and they're balanced. There is 25 newtons of air resistance, friction, air resistance, and the engines are producing 150. So my first step, the black forces cancel each other out, so I don't care about those. Those are vertical. F net is equal to FA plus FF, 150 minus 25. So my net force is 125 newtons. And now I go F net is equal to MA. So 125 is equal to 12 kilograms times A, giving me an acceleration of about 10.4 meters per second squared. All right, so hopefully that helped you. Good luck. Test is coming up soon, tomorrow for this year's class.